Hello and welcome to part 2 of lecture 28. So in the last part we were just looking at this particular example, which is kind of more of a geometric example in R2. Now it looks like it's something special about the plane, but it actually turns out to be something special about any inner product space. So in particular, what we're going to prove is that if we're given any two vectors and if we take some non-zero vector v, and if we set c to be this number, so the inner product of u and v divided by the norm of v squared, and we set w to be this particular vector, then w and v are orthogonal to each other, and what you have is kind of what we wanted. We have the vector u is equal to some scalar multiple of v plus a vector orthogonal to the vector v that we started with. So we can always find this decomposition, which will be sometimes useful in our proof. Okay, so let's prove this. The first part is we're just checking this fact right here, but this follows from just subbing in what we said C and W is, right? So C is the inner product of U and V divided by the norm of V squared times V plus W, which is U minus the inner product of U and V over V squared times V. We look at this and we notice that this term cancels this term, and so we have that this is equal to U, which is what we wanted. Now for the other part, we want to show that W and V are orthogonal. So the way that we do that is, well, what is W? Oops, I erased too many things here. What is W equal to? W is equal to this vector right here. And now we apply our properties of inner products. So this is equal to the inner product of U and V minus the inner product of U and V squared times the vector V with the vector v. And now you can pull out, remember that this guy right here is a constant, so you can pull it out. So we pull it out, and what we get is, oops, that's minus uv over the norm of v squared times the inner product of v with itself. Okay, but remember what the inner product of v with itself is. That's actually equal to the norm of that vector. Squared, the norm of that vector squared. These two terms cancel each other off, and so then you're left with the inner product of uv minus the inner product of uv, which gives you 0. So w and v are definitely orthogonal to each other. Okay, so this little theorem here is actually going to be useful when we prove the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality is kind of one of the big inequalities in mathematics. And its statement is really saying that if you take any two vectors in an inner product space, then the norm of u and v somehow bound the value of the inner product of u and v. So that's kind of one way to kind of interpret what's going on. Okay, and now let me show you how the proof works. So you do two cases, right? It works for all u and v, and we're going to distinguish the case v is equal to 0. Now, when v is equal to 0, both sides are equal to 0, because this norm is 0 and this inner product is 0. So we have equality on both sides. But what happens if v is not the 0 vector? Well, we take u and we write it as the inner product of uv over the norm of v squared times v plus w. Okay, so where we're using the result by the above as by previous result. Okay, so we use the previous result. Now, since v and w are orthogonal by the Pythagorean theorem, we have that the length of the norm of u squared, which is the sum. Now v and w are orthogonal, so we can apply the Pythagorean theorem. So this is equal to the length of the first vector or not the length, I should say the norm of the first vector squared plus the norm of the second vector squared. And now using the properties about the fact that this is a constant inside, when we pull it out, we get uv squared over the norm of v to the 4. Because remember, we're pulling it out, square, right? So we have to square it when we pull it out, this constant. And so we get the norm of v squared plus the norm of w squared. And what we have is that we note that the length or the norm of w squared is greater than or equal to 0. So this is bigger than or equal to uv squared over the norm v to the 4th times the norm v squared, because this thing is just adding some positive thing. And we can simplify this, so we get that the norm inner product of u and v squared over the norm of v squared. We cancel off some copies of the norm of v. So look at the first term and the last term. We can solve. All right, we can solve for this. So what we get is the inner product. Oh, somewhere along the line I lost my absolute value signs. So let me put my absolute value signs in there. There should be absolute value signs here and here and here. And so we have the absolute value of the inner product of u and v squared is less than or equal to the norm of u squared times the norm of v squared. And when we take square roots of both sides, we get the Cauchy-Schwarz inequality. Okay. The statement about the Cauchy-Schwarz inequality had a statement about when exactly you have equality, and you can go see the textbook for that part. But in the next part, I want to show you why the Cauchy-Schwarz inequality is useful.